Okay, the second deep derivative formula we're going to get this semester is the derivative of sine. And as we did before, I'm going to give you a fake answer and a real answer. But the fake answer is pretty good here. The idea is we look at the graph of sine. We know it goes up like this, and then it comes down like this. I want to come down a little bit more, like that. Yeah, that makes me feel better. If that's the graph of sine, what would the graph of the derivative of sine look like? Well, we know how to do this. I know that the slope right about there is 1. So I'm going to put a height here at 1. I know the slope at the very top is 0. So I'm going to put a dot here of height 0. I know the slope right here looks like -1. This is why we estimate these things. I'm going to put a dot down here of height -1. I know the slope right there is 0. So I put a dot here of height 0. I know that when I get back up here, I get the same slope here as I did here. So I make something of height 1 like that. I make sure I graph it like it should be graphed, so with no corners or anything like that. And what did we just graph? We just graph cosine. If someone says, why is the derivative of sine cosine? This is the best possible answer. When you get into Calc 2, you'll see a completely different way of understanding that. But there are infinite processes going on there, and we don't want to get into that just yet. Meanwhile, this is a decent answer for why is the derivative of sine cosine. Now, if you're a STEM major, or in particular a math or physics or chemistry major, that's really not good enough, because that graph could have been anything that curves up and down like that. So what we're going to try to do is to start taking the derivative, by definition, draw a wonderfully large picture, and then come back to what we have. So meanwhile, we have to take the derivative of sine. I'm going to say t, because usually that's the variable we use for sine. So I want the derivative of sine t like that. I know what this is supposed to be. This is supposed to be the limit as h goes to 0. I know there's a big fraction. I know there's an h. I know there's a minus sine t here. I know there's a sine t plus h here, like that, and a minus. And the question is, with all that, what am I supposed to do? Well, if we really want to understand it, what they'll usually do in a regular calculus class is they'll say, remember the angle addition formulas you had in trig. And if they remember them, that's great, but we're trying to understand it. And even if they remember the angle addition formulas, they're not going to remember why they work. So that's not what I want to do. What I do want to do is say, what was the definition of sine again? It's got a nice geometric definition. So what I want to do is take every little part of this fraction and go to the unit circle, because that's where they live, and figure out what each part of this corresponds to, and then we're going to look at the whole fraction, and then we're going to try to work it out. So what I'm going to do here is I'm going to erase this, and remembering what the definition of sine actually is. I don't know that this is going to be big enough. Never have enough room here. In class, I would use 3 boards. This is kind of bad. Okay, there's the unit circle. Remember, that's 1, and that's 1. If someone talks about sine t, what they're telling us to do is go distance t. So we're going to go distance t. Remember, when you're using radians, that means you're calling this angle t as well. What is sine t? Well, sine t is supposed to be the y coordinate right there. We need a little bit more. We need something to look at. So what I'm going to do is draw the perpendicular that goes down like this, and sine t is going to be exactly that height, because that's what the definition of the y-coordinate is. So the sine t is actually just the length of that little piece right there. Now we also had sine of t plus h. So what I'm going to do is I'm going to draw a slightly bigger angle. It can't be too much bigger. The idea with calculus is that you zoom in on stuff until it's straight. Now this looks reasonably straight here, so I can fairly call this h, I think, without breaking too many things. That is going to make this angle, by the way, t plus h. Like that, and we can see that. Yay. Now, what is sine of t plus h? Sine of t plus h says start here and drop a perpendicular right there. And sine of t plus h is going to be that blue distance, that blue vertical distance. So that's the sine of t plus h. sine of t plus h, like that. Now remember, what we're looking at is, for taking the derivative, we have the sine of t plus h minus the sine of t on top, and we have h on the bottom. So what I want to do next in red, we're just going to see what we can get away with here. That's green. Try red. I want the sine of t plus h minus the sine of t. Now, the sine of t plus h was this big blue distance. The sine of t is just this little green distance. So the sine of t plus h is this height minus this height. What I'm going to do is just draw a little horizontal thing right there. And you can see that the sine of t plus h minus sine of t is just that little distance right there. The nice thing is we don't need fancy identities to actually locate it. It's just that little thing right there. Now the really cool thing is when we take the sine of t plus h minus the sine of t all over h, what we're actually doing is looking at this little triangle right here, and it's a right triangle. And what we're doing is we're taking this side and dividing by this side. Well, that's how we define trig functions or fractions of sides. So what I'm going to do is just look at this fraction right here and say, if I can identify what that angle is, right, then this is just going to be the adjacent over the hypotenuse of whatever that angle is. So I'm going to go like that. Now I need to figure out that angle. Now how am I going to figure out that angle? Well, one thing, and it's obvious from the picture about radiuses and tangent lines, is they're perpendicular to each other. So that's going to make this a 90-degree angle. It's going to make this a 90-degree angle. Running out of colors here. That's going to make, oh boy, this one a 90-degree angle. Now, so what? Well, here we go. Ready? I guess I want blue. This angle, right, is t plus h. That's going to make this angle 90 degrees minus t plus h. Like that. That's this one right here. But this angle and our angle add up to 90 degrees. That's going to make our angle right here t plus h. So I'm going to put a little t plus h like that. And this is how Newton would have done it. This is not how Euler would have done it. This is how Newton would have actually done this. Newton was probably better with triangles and circles than anybody in the history of mathematics. Absolutely amazing. But you notice what we're doing here. We're not using anything fancy. We're not using any identities. We're just saying, what's sine of t? Little green distance. What's the sine of t plus h? Big blue distance. What's the difference? Little red distance, right? What's the whole fraction? It's just a trig function of that little tiny triangle. We needed that angle, and we used the picture to get that angle was t plus h. You can come back to this. I'm not going to worry about it. I'm now going to look at what I have in red at the top. Right there, just like that. And actually, let me write the whole thing like this. What we have is if h is tiny. Now, how tiny? Remember, h was just a little piece of circle. It had to look very straight. It's tiny. Then the difference quotient, sine of t plus h minus the sine of t all over h is approximately equal to, let's do it this way, it's approximately equal to the cosine, no, give myself a little more space, of t plus h. We're almost there. The problem is the derivative is not the difference quotient, it's the limit of the difference quotient. So remember, this estimates this. If I take the limit here and the limit here, remember what that does to approximations? You now get equals instead of approximate, which is great. The limit is very easy to calculate. Very first thing we're always supposed to try to do is just plug in. When I put in a 0 for h, I get cosine t. What do I get with all of this? That's the definition of the derivative of sine. So this is the definition of the derivative of sine. So we get that the derivative of sine is equal to cosine. So the graph didn't lie to us, but this is using an awful lot of basic trig. No identities, which is great. Basic trig. And that's how the derivative of sine is cosine.